Hi everybody. Well, now we need to begin our discussion over the CBSE pattern question exercises for the chapter complex numbers and quadratic equations from your 11th standard. First question says find the least positive value of n if 1 plus iota upon 1 minus iota raised to the power n is 1. Now obviously 1 plus iota upon 1 minus iota is representing a complex number with what real part, what imaginary part, we need to decode that, and then we are going to raise it to the power n and find out what is that least value of n for which it gives out 1 as the answer. So if you consider 1 plus iota upon 1 minus iota, clearly in order to decode what is the real and the imaginary part, we are going to multiply and divide by what? 1 plus iota, 1 plus iota. This gives you 1 plus iota whole square whole upon 1 plus iota into 1 minus iota. A plus b, a minus b is a square minus iota square. Minus iota square is minus of minus 1, which is plus 1. So you are left with what? This is what? 1 minus iota square. Iota square is minus 1, so you are left with 1 plus 1. Now this gives you 1 plus iota square plus 2 iota whole upon 2, which is 1 minus 1 plus 2 iota upon 2, because iota square is minus 1. Now in here when I am talking about 1 plus iota square plus 2 iota whole upon 2, because iota square is minus 1, this is what I have got as the expression, and now this turns out to be 2 iota upon 2, which is iota. Eventually what we are getting is that 1 plus iota upon 1 minus iota is coming out to be equal to the complex number iota, which can be written as 0 plus 1 iota. So we have decoded the real and the imaginary part of this complex number, right? And therefore, what eventually we have got is that 1 plus iota upon 1 minus iota is actually 0 plus 1 iota. That is iota. Corresponding to iota, I know that iota raised to the power 1 is iota. Iota raised to the power 2 is iota square, that is minus 1, iota raised to the power 3 is minus iota, and iota raised to the power 4 is 1. For the first time when iota raised to any natural number as power is giving you 1 is 4. The moment you move to iota raised to the power 5, again it would be iota. Iota raised to the power 6 would be again minus 1, iota raised to the power 7 would be minus iota, iota raised to the power 8 would be 1, right? So iota raised to the power 8 would be 1, but the least very natural number for the first time when iota raised to any power, where that power is a natural number, the least such natural number for which iota raised to that particular natural number as the power is giving you 1 is 4. So, and as 4 is the least natural number, as 4 is the least natural number such that iota, least natural number n such that iota raised to the power n is 1, therefore 1 plus iota upon 1 minus iota raised to the power n is actually iota raised to the power n equals 1 for least n equals 4. The least natural number n for which 1 plus iota upon 1 minus iota raised to the power n is 1 is n equals 4. So your answer is n equals 4. Next question says that find the modulus and argument of this complex number. Again we have the same complex number, 1 plus iota upon 1 minus iota. I just told you how to decode the real and the imaginary part of 1 plus iota and 1 minus iota. It comes out to be iota. The moment you have the real and the imaginary part of this complex number, say z, I am saying let z be 1 plus iota upon 1 minus iota, which we know is iota, which can be written as 0 plus 1 iota. This implies real part of z is 0, imaginary part of z is 1. Find the modulus and argument. Modulus of z is under root of real part of z whole square plus imaginary part of z whole square. that is under root of 0 square plus 1 square, which is 1. And if I talk about argument of z, we need to first find tan alpha, right? Let alpha be the acute angle for which tan alpha is mod of imaginary part of z upon real part of z. Imaginary part of z is 1, real part of z is 0, so you are getting 1 upon 0, which is infinity. Alpha comes out to be equal to pi by 2. Clearly, what is happening is real part of z is 0 and imaginary part of z is 1 that is positive. This implies z lies on the y-axis, that too on the positive y-axis. You can see 0, 1 are the actual coordinates in the Argand plane. 0, 1. That means what? X coordinate is 0, y coordinate is 1. So 0, 1 point lies on the y-axis, that too on the positive side of the y-axis. And therefore, principal argument of z is pi by 2. So modulus of z is 1 and argument of z is pi by 2. Let me just show you. This is 0. From here to here, if you measure the distance of 1, this particular point 0, 1 is the point which is actually representing iota, then this particular complex number is actually making 90 degrees with the positive direction of x-axis, and it is 1 unit apart from the origin. So 1 unit is the modulus and 90 degrees the argument. This is where iota is sitting in the Argand plane. Next I have solve this particular quadratic equation. Pretty simple, we just need to compute the discriminant. Let's compute d. Here if I compare it with ax square plus bx plus c equals 0. So on comparing with ax square plus bx plus c equals 0, we have a equals root 5, b equals 1 and c again equals root 5. Discriminant is equals to b square minus 4ac. b square means 1 square minus 4 into a into c. 1 minus 20, which is minus 19, which is less than 0. Therefore, this quadratic equation is going to have what? Two distinct imaginary roots. Therefore, if I say this is 1, I am going to say 1 has two distinct imaginary roots, alpha and beta, where alpha is minus b, so minus b plus root over b square minus 4ac upon 2a, and beta is minus b minus root over b square minus 4ac upon 2a. This means what? Alpha is minus 1 plus root 19 iota upon 2 root 5, and beta is minus 1 minus root 19 iota upon 2 root 5. These are your given two roots. Next question, if we move on to, we have this particular expression given, and that too an equation in the form of complex number z. We need to show mod z is 1, right? Try to think upon it, how basically this equation can help us to get the very modulus of this z as 1, and then we are going to be right back to the same question. So in here basically the point of this particular equation given in the complex variable z is what? If I say that we have iota z cube plus z square minus z plus iota equals 0. The first thing that you focus upon is I want z cube's coefficient to be 1. I need to remove this iota from picture. So what we do, we divide both sides by iota. Please understand one thing. Whenever you divide by iota, you get 1 by iota. Multiply and divide by iota. So you get 1 into iota, iota into iota. Both these are same. This is iota upon iota square, which is iota upon minus 1, which is minus iota. So please remember, 1 by iota always is equal to minus iota. Fine. Now in here, when I divide by iota, I get iota z cube upon iota plus z square upon iota minus z upon iota plus iota upon iota equals 0 upon iota is 0 only. This gives you z cube. 1 upon iota is minus iota. 1 upon iota is minus iota. Right? 1 upon iota is minus iota, minus minus plus iota, and here you get 1. Now what do? You basically manipulate this expression. You write plus 1 as minus iota square. 1 is equal to minus iota square. Iota square is minus 1, minus minus is plus, so minus iota square gives you plus 1. From here you can take out z square common, you are left with z minus iota. And from here you can take out iota common, you are left with z minus iota. So you get z minus iota, and this is z square plus iota equals 0. So here, what is it that you get? Then next is, this implies z minus iota is 0 or z square plus iota is 0. This implies z is iota or z square is minus iota. If z, complex number z is same as the complex number iota, that means their modulus is same, and here these two are same, that means their moduli is same. Right? What is modulus of iota? We just found out in the previous question, it was 1. You can write iota as 0 plus 1 iota, and then modulus would be under root of 0 square plus 1 square, which is 1. From here you know mod of z square is mod z whole square. Mod of minus iota is same as mod iota. You know modulus of z is same as modulus of minus z. So here this is equal to 1. So you are getting mod z is 1, mod z whole square is 1, that means mod z is 1 because mod z is a non-negative quantity. The only quantity whose square can be 1 is 1 when mod z I know is non-negative. So in both cases mod z is coming out to be 1, and hence we have established that if this equation prevails in the complex variable z, then mod z has to be equal to 1. Next we have find real value of x and y for which this complex number and this complex number are conjugates of each other. Now already the relationship between these two complex numbers is full-fledgedly given to you, right? So you are given that this complex number and this complex number are conjugates. Write it in the mathematical format. This complex number is complex conjugate of this complex number. That means this complex number is this complex number's conjugate, bar. This complex number is this complex number's bar. That means when you take this complex number's bar, you get this complex number. That is what is the meaning of being conjugate. That means minus 3 plus iota times x square y is equal to, what do you do when you take bar? You actually just replace the coefficient of iota by minus of that coefficient. So x square plus y, real part remains unaltered, 4 is the coefficient of iota, you replace it by minus 4. That is what it is. Now these are two complex numbers which are equal, that means their real parts are same and imaginary parts are same. Real part of this is minus 3, this is x square plus y, and imaginary parts are also same, x square y equals minus 4. Say this is 1, this is 2. This is also holding and this is also holding, both are holding. From 2, we have that x square is equals to, or rather than that I should write y is equals to minus 4 by x square. Putting 3 in 1, we get, if you put this 3 in 1, you get minus 3 equals x square plus y is what? Minus 4 by x square. So you have minus 3 is equals to x square plus minus 4 by x square. This gives you minus 3 equals x to the power 4 minus 4 whole by x square, which implies minus 3x square equals x to the power 4 minus 4, which implies x to the power 4 plus 3x square minus 4 equals 0. If you for the time being write x square as w, you actually get w square plus 3w minus 4 equals 0. Now it is in the form of quadratic equation. You know how to solve it. Try to break the middle term. You have minus plus 4w minus 4 equals 0. This gives you w plus 4 minus 1, w plus 4. So you have got w plus 4 into w minus 1 equals 0. W is x square plus 4 into x square minus 1 is 0. This implies x square plus 4 is 0 or x square minus 1 is 0. Let me rub this. Okay. First of all, please understand, look at the question again. I want real values of x and y. Complex numbers or imaginary values of x and y are not permitted in this question. So this implies x square plus 4 is 0 or x square minus 1 is 0. But I know that x square plus 4 equals 0 means x square equals minus 4. That means x equals under root of minus 4. That means what? 2 iota. This is going to give me imaginary values of x for which x square plus 4 is 0. There is no real number x which is satisfying x square plus 4 equals 0. But there does not exist any x belonging in R such that x square plus 4 is 0. Therefore, x square minus 1 only can be 0 to make this equation equal to 0. This cannot be 0 for any real x. That means only this has to be 0 so that the product comes out to be 0. That means x square is 1, which means x equals plus minus 1. If x is plus minus 1, y is what? The moment I am saying x is 1, for x equals 1, y is what? If x is 1, 1 square is 1, y is minus 4. And if x is minus 1, if x is minus 1, suppose here you put x is minus 1, this is again 1, so you get minus 3 minus 1, again y is minus 4. So the real values of x and y, which are basically going to make these two complex numbers conjugates of each other, is x1 y minus 4 or x minus 1 y minus 4. These are the values. Next question we have, find the conjugate of this given complex number. Now, please understand what was the drill to find the conjugate of any complex number. Let us write this complex number down. And here when you have this complex number with you, it is 3 minus 2 iota, 2 plus 3 iota, whole upon 1 plus 2 iota and 2 minus iota. Try to simplify. 3 into 2, 6 plus 9 iota minus 4 iota minus 6 iota square, whole upon 2 minus iota plus 4 iota minus 4 iota square. This means plus 6 and this means plus 4. Iota square is minus 1. 6 plus 9 iota minus 4 iota minus 6 iota square. This is 2 minus iota plus 4 iota minus, this is minus, plus 2 iota into minus iota means minus 2 iota square. So, plus 2, right, because 2 iota into iota is 2 iota square, which is minus 2 into minus is plus 2. 6 plus 6 gives you 12. 9 iota minus 4 iota is 5 iota. Whole upon 2 plus 2 is 4. plus 3 iota. 4 iota minus iota is 3 iota. Now what I do is, in order to find the conjugate, I multiply and divide by 4 minus 3 iota, and here also 4 minus 3 iota. What do you get? 12 into 4 is 48, minus 36 iota plus 20 iota minus 15 iota square. A plus b, a minus b is a square minus b square. 48 plus 15 gives you 63 minus 16 iota upon 25. And this is what is the required conjugate of your given complex number. Conjugate of this complex number is equal to this complex number. Clear? Easy enough? Next we have solve this quadratic equation using the general expression for the roots of a quadratic equation. Okay, so here we just need to directly use our formula to evaluate the roots. This is your A, minus 4 is your B, and 3 is your C. Ax square plus bx plus c, discriminant is b square minus 4 into A into C. That is, D is what? 16 minus 4 into 2, 8, 8 into 3 is 24, which gives you minus 18. Isn't it? Because you have, this is minus 8. Clear? If discriminant is minus 8, this is again less than 0. If I say this equation is equation number 1, in this situation, 1 has 2 distinct imaginary roots. There will be no real roots prevailing. Obviously, there will be imaginary roots, and that too 2 and that too distinct. Clear? Say alpha and beta, where alpha is minus b plus root over b square minus 4ac upon 2a, and beta is minus b minus root over b square minus 4ac upon 2 into a. This gives you 4 plus 2 root 2 iota, because root 8 is 2 root 2 and root minus 1 is iota, whole upon 4, and beta is 4 minus 2 root 2 iota upon 4. Obviously 2 can come out common. What will you be left with? If 2 comes out common from the numerator, what will you be left with? 2 comes out common, you are left with 2 plus root 2 iota whole upon 2, and beta is 2 minus root 2 iota whole upon 2. Is it clear? And this gives you 2 upon 2 is 1, root 2 upon 2 is 1 by root 2. This is alpha, and again 2 upon 2 is 1 minus 1 by root 2 iota. These are your two most simplified form of the roots of this given quadratic equation. Next we have find the square root of iota. Now the drill that is used to find the square root of any complex number should be at your fingertips, and then you will be able to decode the very square root of iota within no time. Let's do that. Let z be equal to the complex number iota, which can be written like this. Fine. Now in here, if z is equal to iota, I am interested in root iota, square root of iota. Suppose this is equal to x plus iota y. So iota will be equal to x plus iota y whole square, which is a square plus b square plus 2 iota xy. This is the real part and 2xy is the imaginary part. If iota is equals to x square minus y square plus 2 iota xy, that means real part is equal to the real part, imaginary part equals to the imaginary part. Real part of iota is 0. So 0 is equals to x square minus y square, and 1 is equals to 2xy. After this, what was the step? We always assumed one thing, that x square plus y square whole square, if you simplify, you get x square minus y square whole square plus 2xy whole square. Simply, x square minus y square whole square, that means 0 whole square, which is 0. 2xy is 1, 1 whole square is 1. You are getting x square plus y square whole square is 1. That means x square plus y square is 1 only. It cannot be minus 1. Can it be minus 1? X square plus y square whole square is 1. That means the next step you would say x square plus y square equals plus minus 1, but it cannot be plus or it cannot be minus 1 because x square is non-negative, y square is non-negative, sum of two non-negative terms is non-negative. We have got x square minus y square is 0 and we have got x square plus y square is 1. If you solve these two equations, solving star and double star, x square minus y square is 0, x square plus y square is 1, 2x square equals 1, x square is 1 by 2, which implies x is plus minus 1 by root 2. If x square is 1 by 2, y square is 1 minus 1 by 2, which is again 1 by 2, which implies y is again plus minus 1 by root 2. But we have that 2xy is equal to 1. For 2 into x into y to give you 1, either both x and y should be positive so that 2 into x into y is positive, or both x and y should be negative so that x into y is again positive, so 2 into x into y is positive. If one of the x and y is positive, other is negative, that means x into y will be negative, 2 into x into y will be negative, but 1 is positive. So how can a positive and a negative quantity be equal? Therefore, for 2xy to be equal to a positive quantity, both x and y should be positive or both x and y should be negative. But 2xy is equal to 1, this implies x and y are of the same sign. Therefore, root iota, either it is equal to 1 by root 2 plus iota times 1 by root 2, x plus iota y where x is positive, y is positive, or it is minus 1 by root 2 plus iota times minus 1 by root 2. Both should be either negative or both should be positive. They actually should be of the same sign because 2xy is 1. Is it clear? Next question we have, find the real theta such that this expression is purely real. I need this expression to come out to be purely real. What is that theta which when I plug in this expression, the answer that comes out is a purely real complex number, imaginary part is 0. Let's begin the computation. You have 3 plus 2 iota sine theta whole upon 1 minus 2 iota sine theta. Now, clearly the only thing which directly pops up in the mind is you multiply and divide by the conjugate of the denominator. This is 1 minus 2 iota sine theta, 1 plus 2 iota sine theta, and this is again 1 plus 2 iota sine theta. Clear? 3 into 1 is 3 plus 6 iota sine theta. Just simplify, keep on simplifying, it's very easy. Plus 2 iota sine theta. And then it is 2 iota into 2 iota is 4 iota square, which is minus 4 sine square theta. Whole upon a plus b into a minus b is a square minus square of this, that is 4 iota square sine square theta. Fine. 6 iota plus 2 iota is 8 iota. This is 3. So basically you have 3 plus 8 iota sine theta minus 4 sine square theta whole upon 1 plus 4 sine square theta. Collect together the terms which are not involving the imaginary unit iota and get the real part of this complex number. 3 minus 4 sine square theta upon 1 plus 4 sine square theta. This is the real part plus iota times 8 sine theta upon 1 plus 4 sine square theta. If this is my complex number, for this complex number to be real, for it to be real, the imaginary part has to be 0. That means 8 sine theta upon 1 plus 4 sine square theta has to be 0. This means numerator has to be 0. 8 sine theta has to be 0. This implies sine theta has to be 0. From trigonometry, we know that in trigonometric equations we've done what are the possible values of theta wherever sine theta is 0. Angles which are integral multiples of pi are the only angles whose sine ratio is equal to the quantity 0. So that means theta has to be equal to integral multiples of pi. The moment the theta that is kept in the expression is an integral multiple of pi, this expression is going to result in a complex number which is purely real. Its imaginary part is going to be 0. The moment theta is kept to be an integral multiple of pi. That's it. That's the answer. Moving to the next question, we have convert this complex number in the polar form. In order to convert a complex number in the polar form, we need the modulus and we need the principal argument. First of all, we need to bring it in the simplest form possible so that I can specifically see its real and the imaginary part. So here I am having iota minus 1 upon cos pi by 3, which is 1 by 2, plus iota times root 3 by 2. 2 goes above, you have iota minus 1 upon 1 plus iota root 3. Again I am going to do the same thing, multiply and divide by the conjugate of the denominator. This is 1 plus iota root 3, 1 minus iota root 3. Right? Iota into 1 is iota. Iota into iota is iota square root 3, that is minus root 3. Then you have minus 1 plus iota root 3. Whole upon a plus b minus b is a square minus iota square into 3. Iota square into 3, that is minus 3, so 1 plus 3. Fine. Over here what you have, iota minus iota square root 3, that is plus root 3. Then I had minus 1 plus iota root 3, and here you have 1 plus 3. This gives you what? 2 and this is 4. So in the denominator you are left with 2. You have root 3 minus 1 plus iota root 3. So iota 1 plus root 3 whole upon 2. Iota common 1 plus root 3 whole upon 2, and this is root 3 minus 1. So you basically have root 3 minus 1 by 2 plus iota times root 3 plus 1 by 2. This is your complex number z. This is the real part, this is the imaginary part. So this is real part of z, this is imaginary part of z. The moment I have this, first thing is mod z, which is under root of real part of z whole square plus imaginary part of z whole square. Real part of z whole square gives you what? Root 3 minus 1 by 2 whole square plus root 3 plus 1 by 2 whole square. This gives you what? A square plus b square minus 2 root 3. Then it is a square plus b square plus 2 root 3. This is whole upon 4 minus 2 root 3 plus 2 root 3. 3 plus 1 4, 3 plus 1 4. 4 plus 4 is 8. 8 upon 4 is 2. You are left with root 2. Root 2 is modulus of z. Then in order to compute the principal argument, first I need to compute alpha, for which alpha is an acute angle such that tan alpha is equals to mod of imaginary part of z upon real part of z. So let alpha be acute angle such that tan alpha is mod of imaginary part of z upon real part of z. Imaginary part of z is root 3 plus 1 by 2 whole upon real part of z is Root 3 minus 1 by 2, they are already positive quantities, so I don't need to put the mod sign. 2 cancels out. This is root 3 plus 1, root 3 minus 1, take out root 3 common, 1 plus 1 by root 3, 1 minus 1 by root 3. Now see how beautifully we try to convert it in the tangent format. 1 can be written as tan pi by 4, 1 by root 3 can be written as tan pi by 6, 1 minus tan pi by 4, tan pi by 6. Tan A plus tan B upon 1 minus tan A tan B is tan of A plus B. Pi by 4 plus pi by 6. Right? If you take out LCM as 24 also, you are left with 6 pi plus 4 pi, that is 10 pi by 24, that is 5 pi by 12. So this is tan of 5 pi by 12. If tan alpha is tan of 5 pi by 12, alpha is acute angle, tangent is a 1-1 function in that particular domain area, that is 0 to pi by 2, it is a 1-1 function. So tan alpha equals tan 5 pi by 12 means that, what does it mean? The alpha acute angle is 5 pi by 12. But depending upon the sign of the real and the imaginary part, we decode in which quadrant the very complex number is lying. According to that, we manipulate the very principal argument of z and conclude about it. So as real part of z is positive, you know that it is this. Imaginary part of z is also positive, you can see. Therefore, z lies in the first quadrant, and therefore principal argument of z is equal to tan alpha itself, or principal argument of z is equal to alpha itself, which is 5 pi by 12. The moment I have root 2 as the modulus and I have 5 pi by 12 as the principal argument, I am in a position to write the polar form of z. Therefore, polar form of the given complex number z is mod z cos of principal argument of z plus iota sine principal argument of z. And that completes our discussion over the last question. Thank you. That's it from my side.